Perfect. I keep the door open. If there is noise later on, I just kindly ask the last one of you in the bottom of the room to close it. Okay, and let me just open a little bit the window. The curtain, if you feel comfortable, it's too cold, just let me know, okay? Perfect. Okay, let's go to our tutorials. I started to talk about sustainability in the 21st century last time. Let me go to this page because I didn't finish. Let me get the PowerPoint. Very good. I need to share the screen for those who are at home. Just 1 second. At home or remotely connected. One second. Okay, good. Let me share the screen. Okay, so last time we started talking about sustainability and sustainable development, and the key concept that I highlighted is that it was a very good idea to reconcile two terms that were considered to be antithetic at that time, sustainable and development. The idea was just to try to marry them, to put them together. And I said that there were several alternative definitions that were given for sustainable development. Actually, what I did before coming to the definition was to summarize a little bit the history, an history that started from 1968, from the first Water Charter of Europe, and then it moved on through a series of international conferences. And I mentioned Rio 92, which was repeated after 10 years and after 20 years, Rio 2002 and then Rio 2012. I didn't mention several other conferences because I don't think it is really important that we know the details. We are studying engineering, we are not studying history or philosophy of science. But in the web page, there are many more details. So if you are interested, please refer to that. At the exam, I will not ask what was the conference that proposed the definition of sustainable development. What I instead may ask at the exam is the definition. And I realized that last time I told you that there are several alternative definitions, but I didn't explicitly tell you what is the accepted one, the one that is now accepted as definition of sustainable development. And it's here, so let's read it. And it was defined by a commission, which is called the Brundtland Commission, because the chairman was a guy whose name was Brundtland. And the definition reads as, sustainable development is development that meets the needs of the present without compromising the ability of future generations to meet their own needs. So just please keep it in mind, because it is very simple. If you're asked a definition for sustainable development, you don't need to repeat it word by word, but you have two key concepts to keep in mind. That development means that you try to meet the needs of the present generations, but at the same time, sustainable means that you look at the future. That's it. And basically, it contains two concepts, as you can see here. The concept of needs, and in particular, the essential needs of the world poor, and the idea of limitations imposed by the state of technology and the social organization of the environment's ability to meet present and future needs. Two things. When this concept emerged, the sustainable development, we humanity started to realize that there is an essential ingredient to meet this requirement of sustainable development, which is diversity, equality, inclusivity. There are three words, actually. These are three words which can be unified in what is called the EDI concept, equality, diversity, inclusivity. This is essential, and it's not mentioned here. It's a concept that is continuously taking off and getting more and more popular with some sensitivity related to it, and it's clear that it's a sensitive concept. But I think that as engineers, we need to understand, even if it's not really a matter for your exam or for your technical design, but we need to understand why, indeed, equality, diversity, and inclusivity are essential ingredients. It's not just a buzzword. It's not just a say to demonstrate that we care about the poor. It's really a technical consideration, a conceptual consideration, because think about pandemics, for instance. You cannot resolve the problem if you don't treat the problem at the global level. If there are some countries still suffering from a pandemic, then the pandemic continues to spread, of course. And the same for poverty. If you have countries suffering from poverty, then it's a problem for everybody. Why? Because these countries, of course, they claim their own rights, and they migrate, and then they create, of course, some kind of discomfort where they go. They create some kind of economic imbalance where they go. Because, of course, if there are people that suffer from poor conditions, it is a problem for all of us. And therefore, this is one reason to convince you that indeed, if we want to develop our society, we cannot develop it only in one place. We have to take care of a global perspective. We have to adopt a global perspective. Of course, we cannot say that we succeeded so far. It is very tough. I think that it is indeed difficult, because think about water. Water cannot be moved. In principle, it's very complicated to move water. So how to bring water to the countries where they suffer from aridity? Taking water from countries who have a lot of water. There are many countries who have excess of water. So it's impossible to move it. Or you can move very small quantities, but you cannot move large quantities. So it is indeed something that is difficult, technically difficult, but we have to understand the key value of the concept. And again, once again, if you suffer from, if it is too cool, just tell me, okay? So this concept of equality applies not only in terms of economics, it also applies in terms of balance from over different categories of humans: gender balance, geographical balance, ethnic balance. It is an essential ingredient. Otherwise, if we don't adopt this wide perspective, we cannot succeed. Okay, we can get some temporary benefit, some local benefit, but then it will be a problem. And our everyday experience confirms, if we look at the international situation, that where there is inequality, where there are people suffering from poverty, there you have wars, you have social tensions. And the same for the lack of water. Water has been proved to be an important driver for social tensions, for wars. There are several examples. Okay, so we have then this definition. There are alternative definitions which I showed you last time of sustainable development. It is just enough that you keep in mind this one. It is very simple. Have a look on my webpage if you are interested in what have been the subsequent attempts to better clarify what we mean. You will not easily find an explicit reference to EDI, as I mentioned, because this is something that is really taking off now with a lot of power. So just keep in mind this. Okay, now, this figure I already showed to you last time. These are the pillars of sustainability that have been recognized by these international conferences. And these pillars here, you see that they are put inside each other. because in a way, previously, they were considered to be antithetic. So if we look at economy, you know, some people saw some conflict with society and the environment. Societal development means environmental impact. So these pillars were considered to be antithetic, and the idea was instead to try to reconcile them. And in particular, there is a subsequent figure, I think it is in the next slide, let me check, this one, which I think it is very, very instructive for us. Shows that the three pillars indeed have intersections, and we have to maximize these intersections. And I think here the interpretation is interesting because you see that the intersection between the social and the economic pillar identifies what is equitable, okay? And the intersection between the social pillar and the environmental pillar identifies what is bearable. The intersection between economic and environment basically identify what is viable. And the intersection between the three pillars identifies what is sustainable. Okay. I feel guilty, so let me just close a little bit, okay? Because usually I don't suffer the low temperature, but you know, I saw many of you that are putting jackets on, so I don't want to. I want to make the lecture sustainable. Okay, so I think this is really interesting because it shows what we have to achieve. We have to maximize the intersection between the three pillars of development. These are the three pillars of development and sustainability, and we have to try to maximize the intersections among these pillars. Okay, now let me just go back to the web page because I want to make sure that I'm not forgetting anything. Just 1 second. I am more or less here. I am almost done with this concept, but okay, perfect. Now it's the time of the Sustainable Development Goals, because I am trying with this lecture, to give you an overview of the development of this concept. And in 2015, the United Nations approved the so-called Agenda 2030. And they identified the Sustainable Development Goals. And I think that you know them. And this is not, again, notion for the exam. I just want to remind you what they are. And in many, today, when you propose research projects, when you propose educational initiatives, we are frequently required to identify the Sustainable Development Goals that we aim to achieve. We aim to contribute to achieve with our initiatives. Keep in mind that each of these goals has sub-goals, and you can easily find them. We are not discussing these. You can find here the concept of equitability, diversity, and the concept of inclusivity. You can identify the role of water, the role of climate change, and many others. There is some discussion and criticism around these goals because you can understand that these international initiatives sometimes are conflicting with the national interest of countries. And sometimes some people think that these global initiatives are a way to force some kind of political development. So you may hear some discussions about these. Some people saying, well, I really don't like this because it looks like a nice picture, but actually what are the countries doing? What are the big countries doing for achieving this? They are just paying lip service. You understand what is lip service? Just talking. And then there is some discussion. Actually, I think that indeed, if we look at real actions, there might be some room for criticism. So if you look at the real actions that the countries took so far, or also the real technical achievements that we had, indeed, I'm not sure we can say that we are happy. These are already 7 years old, and we are at the mid of the path towards 2030. So I'm not really sure that we can say that we are at a good stage now. But we have also to consider that, there are difficulties and there are opportunities that may arise very quickly. So I want to give you an example. One topical issue is the reduction of the CO2 emissions in order to mitigate climate change. And of course, one relevant problem is energy production, because development means energy. We need more and more energy. And now we are producing energy, I think 80%, still 80% with fossil fuels, still now. I mean, the renewable at the global level are about 16, 17. We will see these numbers because in our subsequent slides, I show you these numbers. So basically, you know that there is an effort to increase the percentage of energy that is given by renewables, but this is costly. And the result is that our bills, our energy bills went up. This is one of the drivers of the increase of the bill for energy and other public services. Not the only one, actually, because there are also international tensions, the price of gas from Russia, et cetera, et cetera. But still, the investments that we are doing on renewable are a bit demanding. So the question is this sustainable actually? So we are trying to go towards renewable energy because we want to make our energy production sustainable. But is it sustainable, the renewable energy, with respect to people? Because there is one thing that we often miss. We think sometimes that politicians just look at their popularity, but sometimes there are also politicians who look at the welfare of the country. And so, renewable, on the one hand, they are they are a resource. On the other hand, they are very costly. And basically, only very rich countries can afford the price of renewables. And the question is, why don't we wait a little bit? Because it may be, you may have heard a couple of, I think 1 week ago, that in the UK, I think in the UK, they made a successful experiment of nuclear fission, and which may open the door to really something really revolutionary in terms of energy production. So, and this may happen within few years. So is it worth spending money in solar panels or wind energy production, wind farms, sorry, I couldn't get the term, which have an environmental impact, because you know that there is a huge environmental impact related to wind farms and solar energy production, solar farms. And so the question is, what is the best solution for this? And this is a question for engineers, interdisciplinary, because of course we need to know, for instance, hydroelectricity is related to us, is related to environmental engineering. And to some extent also wind farms and solar farms are related to environmental engineering. But nuclear fission and nuclear energy is related to another kind of engineering. So it's interdisciplinary engineering. And it's not easy to find the correct answer. So sometimes the fact that we don't take any action is not just related to the lack of will. It's related to the fact that there is uncertainty in the future. There is the famous say, making prediction is particularly hard, especially if they are related to the future. And there are uncertainties, and taking a decision is not easy. And it's our role to try to become experts on this and provide an objective assessment. I really think this is an opportunity for you, for all of us, but for you in particular, because you have more time with respect to me. But in order to transform these challenges in opportunities, we have to refer to our individual background. Our background is engineering. We decided that our background is engineering. And therefore, we have to focus on the technical solutions and become expert not just in the opinion, in the social opinions, but we have to try to become expert in technical solution, which means devising them, because we don't have in most of the cases the technical solutions yet. Sometimes we think that we have the solutions, but somebody doesn't want to apply them. So some people think, why don't we invest in renewable energy? I explained you why we don't. Why it's not advisable to just go that way. So what is really lacking in many cases is the technical solution. And this is also related to mitigation of climate change, adaptation to climate change. Everybody tells me as an engineer, tells you as future engineers, you have to do something. You have to take into account climate change. You design a bridge, take into account climate change. But how? How? This is still an open question, okay? Which opens the door to your contribution and explains also the role of science, of research. And you don't have to think that this is not for you. You can contribute to this already now, okay? The important thing is that you become aware of the topic. You become aware of what has been done, what has been achieved already, what has not been achieved already. I try to give you some of my interpretation, some overview, but actually I don't have time to, this is just 48 hours. I try to give you some suggestions to expand your knowledge. The suggestion that I give to you, are you interested in sustainable development? Just try to look at the technical aspect of it. And don't underestimate your capability already now to say something new, to deliver your interpretation. Of course, before that, you need to study, you need to learn what has been done, as I said, what still has to be done. Okay, so I think we can skip this. I really think that engineering can give an essential contribution, and be aware of that and be proud of that, because sometimes in the public discussion or in the media, sometimes we think that this is not something for engineering. Sometimes we think that the engineers, I'm not sure if I already made this reasoning with you, because I'm teaching other two courses, so forgive me if I'm repeating. Sometimes the public and the media think that engineering is the guilty guy, the guilty person, because, of course, the environmental impact is caused by infrastructure, by structures which are designed and in a way promoted by engineers. So sometimes some people think that the role of scientists is just to fix what has been broken by engineers. And this is really not a nice interpretation, because actually engineering is responsible for development. It has a key role in development, together with economics. But you understand that if we have to design an innovative project, an innovative technical project, this is something for the engineer, because we have the background for doing that. And engineering has also a fundamental role in finding the technical solutions to ensure that the development is sustainable. So I think engineering indeed has a fundamental role. And I say this not to protect my field, but just to make you aware of the opportunities that you may have in your future. Let me just skip this. And this is cut and paste from the web pages. You can read this. You can read there. Okay, now let's go a little bit more into water and the role of water in all of this concept. I think the FAO, which is an international organization, Food and Agriculture Organization, I think this is the extended name. FAO is an international organization which has its mission is to promote the accessibility to food to everybody at the global level. So Food and Agriculture Organization, and if you are interested in a more detailed description, they have a website. The mission is stated there better than what I'm doing now. But what I just want to emphasize from our point of view is that they are collecting data on water resources and food production, and they are making research also on strategies in order to promote accessibility to food. And they had this nice idea to identify that water, food, and energy are intimately related. And the connection between water and food is clear. The connection between water and energy is given by hydropower, hydroelectricity. Keep in mind that hydropower, we will discuss it later, it's an essential key of sustainable development. We will see why. It is underestimated, the role of hydropower. We will see why it is essential. And therefore you can understand the whole connection. And also between food and energy there is connection, because a very consistent percentage of renewable is produced through biomasses, which are related to food production to some extent. This concept, again, it's not something that you need to study for your exam. Just you need, in a way, to be aware of the fact that I give you just an anticipation of a number. If we look at the water that is consumed by humans, 70% is for food production. So you understand that if we talk about a water problem, we talk about a water for food problem. So it is, it's not a problem to get the water to take a shower or to flush the toilet. The problem is water for food. And this is also, it's not only in the poor countries. This is a global percentage, and if you look at Italy, it's exactly the same. I think I already mentioned this to you. Okay, and now let's talk about energy then. Okay, and let's talk about, because if sustainability is strictly related to the water, food, energy nexus, let's look at energy production, and let's also give some numbers later on water for food. Now, let me just see if, no, I'm not missing anything so far. Okay, let's look at this graph. These are the numbers that I wanted to give to you in order that you get an idea. And it may look strange to you if I'm talking about energy now, but as I said, there is a tight connection. If we talk about sustainability of water system, we have to talk about energy sustainability. And I will explain you later in more details. Okay, let's see. I open when we close the book. Now, essential information. This is related to data 2010. It's not changed. Okay, it changed a little bit, but just tiny changes. So, energy production, you see on the left, total energy production. The total fossil fuels, 80%. Keep in mind, so some people say, some politicians say, by 2030 we will relying 100% on renewable. It's not possible. It's not possible. Let's just be clear on that, okay? It's not possible by 2030. Renewables, 16%, 17. Now I think it increased a little bit. I think we are around 17 point something. And the nuclear, about 3%. Okay, let's look at the renewables then. Exploded here, okay? Biomass produced, used mainly for producing heat, 11%. Look at the other percentages, really very, very tiny. There is hydropower, 3%, which emerges, but the other percentages, solar, wind, I think that wind now is close to 1% of the total. So when I listen to some people saying Wind energy, we will rely on wind energy and we can produce all the energy that we need through wind. It's not possible. It's absolutely not possible. What looks more promising to me is nuclear. Nuclear, you know that there has been a strong debate in the past. There are some countries relying on the use of nuclear energy. It is dangerous, but in the future it may be possible to use nuclear energy without relevant risks. Keep in mind that there are risks associated to any energy transformation. Okay, and of course, if you build a dam, there are risks. Of course, the mission is to limit them, but there are risks also in the natural environment. So, I mean, it's not a problem to take some risk associated to nuclear energy. The problem is that the risk has to be under control, has to be comparable to the risks that we normally accept in our everyday life. But I think this is potentially very promising. The other sources, even solar energy, even if we improve in the technology, etc., I think it is it's still very, very, very low. I mean. And these numbers are really, you can find easily an update. There is, I don't remember the name of the website. I think it is the World Energy Balance. If you look on Google for World Energy Balance, you get the numbers to 2020. And they are very similar, even if, indeed, in the past 20 years, there has been an increase of renewable. If you go back to 2000, 20 years ago, the renewable were not 16, they were around 10. So, I mean, we doubled it in 20 years, but still, doubling means 10% more, 8% more, which is not really promising for the near future. Okay, another interesting this is the slide that describes, I think there is a detail which is nice to highlight here. At the national level, at least 30 nations around the world already have renewable contributing more than 20%. Not much more than the average, but this is to be considered. It depends on the investments, and it depends, of course, on the resources, because some countries have a lot of water, like Italy, for instance. Hydropower, for sure, it's greater than 3% of I don't remember the percentage, but I think in Italy it's more than 10%, the national use of electricity covered by hydropower. And but still, of course, it depends also on the resources, as I was saying, and but still, it's quite low. There are no countries that can rely on more than 20% on renewable. Okay, this is the total energy production by countries. I don't see here. Okay, the colors are here. I remember that yellow is China, and if you look, for instance, at China, it increased a lot the energy production, but this is a known result. But all the countries increased because they need to cover the energy demand, which are steadily increasing, which is a good thing. But still, it's you see that there is disparity. There is disparity, and disparity in the energy production. You know, it's true that energy can be moved. For instance, Italy takes a lot of energy from France because they have nuclear energy, which is more developed, and therefore they have energy to sell. Energy can be moved. It's not like water, but still, if there are these disparities among countries, this is not a really good a good indicator of equality. I'm curious, I don't remember. The red one is, let me see, green is Europe, dark is green, South America. No, the red one is the global, sorry. It's the global. Let me see, the left, the right. Yeah, it is the global. The red one is the global, and beware that there are two axes. So the global refers to the left axis. The individual countries refer to the right axis. Okay, this is why because I had in my memory that the red was the global, but I couldn't understand why it was lower than one single country. The reason is that the country graphs refer to the right vertical axis. Okay. Now, let me just check the web page. I want to make sure that I'm not forgetting anything. Just 1 second. Yeah, but I think just let me check. I'm okay, perfect. Sorry for this. I go back to the previous slides. I just wanted to make sure that I was not missing anything. Let me check. Okay. Do you have any questions so far? I don't think so, but okay. Now let's talk about sustainability and water resources management. Now we are getting more specifically into water. As I said before, I anticipated that I would speak about energy and then about water. So how can we define sustainability for water resource systems? We can define it in this way, as you read in the first item up there. In the context of water resources management, sustainability can be defined as the property of water resources systems to remain functional in the long term. And it refers, this definition, to the global plurality of water resource systems, and then what is the implication? The implication is that there is an essential premise that we have to make when we talk about sustainability of water use and water resource systems. We have to take a global perspective. This is new, because up to a few years ago, water was considered, and still is considered by some media and some interpretation, a local problem. Given that water cannot be moved easily, water has been always considered a local problem. And this is one of the reasons why, as I already mentioned to you, I think, probably water change is not considered as a critical problem like climate change is, because it's considered to be local and the solution has to be local. So water problems are considered to be a responsibility of local managers and not of global politics, global management. Actually, we need to change this interpretation, because only by taking a global perspective we can consistently resolve water problems. You may say, this is impossible. One may say this is impossible because you cannot move water. And keep in mind this concept, because it's counterintuitive. We are talking about, we will see the numbers. When we talk about water consumption, we are not talking of a bottle of water. The bottle of water can be moved. If you want to move millions of cubic meters of water, you need big pipes and long pipes, because one thing is to move to 200 kilometers. We do that. We make water supply systems, and also the Romans did, that were tens, hundreds of kilometers long. But you cannot move, you cannot make them long 2,000 kilometers. You cannot bring a lot of water from Sweden, where they have a lot of it, to Italy, to the south of Italy. You can even not move water from the north of Italy to the south of Italy, because you would need a huge pipe and a very big one, and you would need a lot of energy. A lot of energy. I mean, water is heavy. This is another issue. Not only its big volume, it's very heavy. If you try to lift 100 liters of water, the weight is, what is the weight of 100 liters of water? 100 kilograms, correct. Okay, because it is not so, I realize that the weight of a liter of water is not so, but in engineering, people know that. If you ask the same question in other faculties, they have a little bit of hesitation. And so it is very heavy, and you need a lot of energy, because you have to cross mountains. So either you dig galleries, sometimes we do that, in order to save energy when we have to move water, we dig galleries. Otherwise, if you want to cross mountains, you need a lot of energy. And also the fact that it's very heavy implies that the forcing on the pipes, on the structures, it's an important forcing. If you look at the pipes bringing water from upstream to downstream for hydropower production, you see big things. So one may say it's impossible. No, it's possible. I will tell you why we need to go this way, to take a global perspective. Because there are now emerging possibilities to move water. And so, what are the technical requirements then? If we talk of sustainability of a water resource system, and we want to talk about technical issues, what do we have to consider? Here there are some suggestions which you may expand. Lifetime. There are some water resource systems that are hundreds of years old, and I tell you an interesting story. In the well before, in the Roman time, the Romans in Bologna built an aqueduct that took the water from I think it was from the Setta River, which is I don't know what is the distance, but if you look in Wikipedia, Roman aqueduct Bologna, you find the whole story. It is very interesting. They built this aqueduct, taking water from fresh water from upstream in a river, and bringing the water to Bologna. And the Romans didn't have pumps and didn't know about siphons, which allow us today with some water supply systems to bypass, to cross mountains without implying a lot of energy. But the Roman used only open channel flow in their water supply system. So this is why you see these big bridges in the center of Italy, because they wanted to keep the elevation of water. They didn't use pipes to transport water. They used only open channel. So to reach Bologna, they had to cross an elevation, a mountain, and they dig the gallery into the rock. It is something that it's from an engineering point of view, it's amazing, because it was digged by hands, perfectly shaped, and they used this. Good. Then the Roman Empire collapsed. And in the Middle Age, you know that there was a new period of prosperity in Italy, and the cities basically started to develop again, and the life and the social life, water requirements, but they didn't have the water supply system because it was completely forgotten, and never more used after the collapse of the Roman Empire. And they decided to take water from the underground, which the Romans didn't do. They didn't use water from the underground extensively. Okay, they had some wells, but not really many. While now we are taking a lot of water from the underground, still now. The majority of the water that we use in this region is taken from the underground. Now can you please close the door? Thank you. Okay, let's try. And of course, in the Middle Age, they didn't put the well very deep, and they were very superficial. Because originally, but even now, if you make a well here in this region and you go down just 10 meters, you already find water. So they had these wells, but after a while, you know, the social development, the water became contaminated and there were pandemics. And when they understood that, at the beginning they didn't understand that the pandemic was coming from the water that was contaminated. They didn't understand that. And there is a nice history on if you look at Wikipedia, there is a nice history on how they discovered that the big pandemics of the Middle Age were caused by contaminated water, because they didn't know. At the beginning, they thought that it was coming from the air. And if you look in Wikipedia, Broad Street Pump, London, there is the story of how a medical doctor discovered that the problem was the water, because there was, during a pandemic in London, there was this doctor who didn't understand the reason for the people dying, mapped on a map the number of deaths. And he realized that they were around, most of them were around a public pump where people went to take the water. And another thing that he realized is that there were no deaths inside a monastery. And he wondered why. The monks were completely immune. So basically, by looking at the pump, he discovered the problem was water, but then he wanted to understand why the monks were immune. And then he went there, and they said that they were not drinking water, they were only drinking beer. And this looks like something funny, but it's true, because they were beer makers, and for some reason, they didn't drink water. In Bologna, there was a similar problem. They had the pandemic, and the water was also badly tasting, but they didn't realize that the problem was the water. And in order to try to mitigate the bad taste, the wine industry, also for seeking a commercial, of course, a commercial benefit, they decided to mix the water with the wine and to sell wine mixed with water. But this didn't solve the problem. I mean, because only wine, probably they would have solved the problem. But of course, the wine is not like the beer, it's very alcoholic. So, and to maximize the profit, they decided to make a mix. And this solved the problem of the taste, but not the problem of the pandemics. But then in Bologna, they realized this, and they realized that they had to find an alternative way of taking water. And then there was an archaeologist who made an historical research and discovered that in the Roman time, they were using this aqueduct. So he explored the land and found it, and it's still used today. We are still using the Roman aqueduct that was rediscovered after about 1,000 of years that was forgotten. This is a really nice history, so I'm just reporting it to you in order to take a small break. But I think it is very interesting if you look at the history of water resource system, the history of engineering, you find useful indications on how the problem have to be solved today, with a very practical attitude, by looking at the past, what people did in the past, because sometimes we assume that all what was done in the past was wrong. This is not true. Actually, if humanity has a history of millions of years, it means that overall, the strategy of our development was fine. Okay, and the lifetime societal development during the lifetime of the system, this is also something that you have to consider. Changes in water resources status during the lifetime of the system, which may be due to climate change, and resilience of the system to societal development. Resilience, you know what is resilience? Is the capability of a system to recover after a shock, to quickly recover, efficiently recover after a shock. I say that I am resilient if I experience, for instance, a sudden accident, and I am prepared to recover from it. If you make an insurance, you become more resilient, because of course you have the means to recover if something happens. And some water resource systems are resilient, others not. And think, for instance, about the capacity of expansion. So do we have additional sources of water for Bologna in case something goes wrong, in case a well gets dry? Or are we, as we say in Italian, alla canna del gas? It means that we have already exhausted our possibilities. And afterlife of the system, today there is a topical issue in engineering: renovation of water resource systems. Our water resource systems are old. Of course they are old. And the question is, should I renovate? Should I build new ones? Sewer systems are old. Water resources systems are affected by leakages. We need to reduce the leakages. How to renovate? Interaction with governance. And let me skip this. This is just social learning is something that I already discussed. It means that, today engineering is also communication. We already discussed this, and it's on the web page. Let's skip this. And now let me just spend some time on this. I said that water cannot be moved. Actually, there is a way to move huge quantities of water. It is what is called virtual water trade. This concept was introduced very recently, or let's say at the beginning, it has a long history, but it has become popular in the past 15 years with the introduction also of the concept of water footprint, which I will introduce in the next slides. What does it mean, virtual water trade? It means that, as I said, water means food. Water consumption, water scarcity means food scarcity. An alternative to moving water is moving food, or moving goods that need a lot of water to be produced. This is the virtual water trade. So instead of moving water, why don't you move food? You may have heard that China is buying a lot of fields in Africa, in water-rich countries, because they want to produce the food there and then bring the food to China. This is something that is criticized because one thing is to import, one thing is to buy the land in other countries. And if it is done in a massive way, you understand that may originate disparity, because maybe the country is poor, you buy, of course, countries that have a lot of money can buy their resources. But if you buy the resources from another country and maybe that you underpay them, of course, poverty is increased. But the virtual water trade, conceptually, it's very interesting, because it means that countries that have a lot of water can export the food. And in order to avoid disparity, you have to, in a way, control this, of course. And which is a sensitive issue. When you use the word control, controlling something, of course, it is a sensitive term, because controlling may also mean that people are in a way controlling your business, controlling your life, controlling. So it is something that it is sensitive, but still, ideally, let's say ideally, in an ideal world, the share of resources is the way to ensure equality. Now, the virtual water trade, water footprint. This slide, I think it is really nice. I'm sorry that you can't really see it, but let me just show single parts of it. Okay, I expand the slide on the screen and I show single part of it, because I think it is really interesting. It is nothing for your exam, but still, I mean, it is very, very interesting. Okay, first of all, the figure gives a lot of information, really a lot. And let me focus on what we already know. 70% of existing fresh water is withdrawn for irrigation in agriculture. Look at what is on the screen now in the bottom right. Good. We already discussed this. Let's look at the left, the many drops. On the left, you have 100 drops, which basically depict the amount of fresh water available, okay? And with respect to the salt water, the light blue is salt water. You see there is the legend on the right. It's difficult to read on the screen, but this is salt water. In a way, 97% of the water is on the Earth system is salt water, cannot be directly used for human consumption, okay? 97%, which means that if we were able to desalinate efficiently, we would have solved any water problem and water engineering wouldn't exist anymore, almost, okay? But now it's not possible. We can desalinate, but it requires a lot of energy, and also it implies a lot of waste, the production of a lot of waste that has to be displaced in some way. You cannot bring back the salt in the sea, or if you do that, it has to be done with particular care. You cannot just throw into the sea a mountain of salt, because you would increase local salinity and cause ecologic disasters. Okay, so it's not so easy to use this salt, to displace it. Now, of the 3 remaining drops on the bottom right, there is 1 drop which is the dark green, readily available fresh water. So only 1% of the total water in the Earth system is readily available. 1 drop is fresh water stored in ice caps, is not really readily available. And the third one is, 2 drops are in freshwater ice caps. So 2% of the global amount of water is in the ice caps, and there is 1% is readily available. Still, it's enough for the human consumption currently and also in the own future, even if we assumed that there is an increase of the world population to 8 billion or 9 billion or whatever, it's still the only 1 drop, only 1% is still enough. The problem is the space-time distribution. In order to be used, we need water where we need it and when we need it. If I need water for food, I need water during the dry season, during the summer here. During April, the food season is April, September. If I have a lot of water during the winter, it cannot be used for that. I need something. I need an engineering solution to store the water and reuse it when I need it. Or this is for time. I mean, if I want to move water in time, I need to store it. If I want to move water in space, I need to transport it, which is not easy. So even if at the global level, we can say that even in the current condition, we have enough water for everybody, still, yes, we need management, correct. Still, I was saying, still, there are water problems. Why? Because we need management, yes. And for this reason, we study water resources management and et cetera, et cetera. Now, let's look at other numbers. The big picture of the world clarifies the water footprint per capita. What is the water footprint? Is the amount of water that is used within that country for producing food and essential goods. For instance, if one may think that producing food is just related to agriculture. Not only. Even producing meat, even producing pasta, you need water. Okay? And also, in order to produce suits, shoes, you need water. So you see basically in dark blue the country that use more water. And in light colors, the country that use less water. Of course, they use less water because they don't have it, probably. Or because they have it, but don't have the means to use it. And so, some countries import water through the virtual water trade. And here you see the countries that are importing more water. Kuwait, and sorry, it's not really that they import more water. This is the percentage of water import over the total for these countries. So Kuwait imports 87% of the water, but in terms of volume, probably it's not very much. Okay, Malta, 87%, because probably they don't have enough water resources to use in Malta. Netherlands, 82%, Bahrain, 80%, Belgium, 80%. And now, interesting, these circles that now you see in the middle of the screen, and it shows the highest water footprint per capita. United States, 2,400 cubic meters per year per capita. Okay, 2,400 cubic meters per year per capita. Now a more difficult question. 1 cubic meter of water, how many liters it is? Correct. This is more difficult than the weight. So you understand that if you want to know the liters here, you have to put 3 more zeros, okay? Which means 2 million. In fact, I said millions before because I was thinking the liters, 2 millions and 400,000 liters per capita per year. Okay, even if you divide by 365, it means a huge amount of water. This is different from the water that is actually consumed. 2 days ago, 3 days ago, I mentioned to you that we are designing water supply systems in Bologna for 400 liters per day per person. But water footprint is more than that. Is the direct use plus the use for producing the food. And now some numbers of water footprint for producing some goods. These numbers are amazing. You can believe that. You can't believe in these numbers. 1 kilogram of chocolate, 24,000 liters, 24 cubic meters of water. 1 kilogram of beef, 15,000 liters. Beef and meat production is a relevant source of CO2 emission, as you know, but also water consumption. 1 kilogram. And you know that once I gave a talk at public forum, it was called a Reddit forum. I don't know if you are aware of this opportunity to participate to forums that are given by the TED Talks or the Reddit Talks. The Reddit Talk is interactive. So it's basically a forum where I don't remember. I experienced it some years ago, and I don't remember. But I think that I made a presentation available, and then after 2 hours, I had to make myself available for 1 hour for questions. And the presentation was about this. And a farmer asked a question because a farmer from the United States, he said, I can't believe this number. I tell you, if you come to visit my farm, I don't use water. And I replied by saying, you are just looking at the water that you take from the tap, but you are not considering the energy that you are using, and energy production requires the use of water, at least for cooling the system, if it is a fossil fuel energy, as it is likely it is, and et cetera, et cetera. So it is a number that is difficult to believe, but I tell you, this has been proved in scientific papers, so I really trust these numbers. 1 kilogram of olives, 4,000 liters. 1 kilogram of sugar, 1,500. 1 cup of coffee, 140 liters. And one may say, but why is that coffee? It's because coffee, you need to irrigate. To produce the coffee, you need to irrigate the plants. So it is really, I mean, something that is interesting. Interesting because it clarifies in which ways we are using water and how you can import it. So if you import meat, if you import chocolate, you are actually importing water. Other numbers here, and it is the highest renewable water resources So more than 2.8 billion people in 48 countries will face water scarcity condition by 2025. This picture is about 5 years ago. And by the middle of the century, this will have reached almost 7 billion. Keep in mind that these predictions, when you see predictions, one thing is numbers estimated on data, okay? When you see predictions for the future, you are an engineer, you have to become skeptical, and you have to, not skeptical really, critical. And you have to immediately wonder, what is uncertainty? You are an engineer, when you are given an information, when you are given an observation, you should immediately react by lighting in your brain a bulb, uncertainty, because this is essential. And so basically this estimate, when they go forward 30, 40 years, uncertainty is really, keep in mind that when you talk about environment, when you talk about society, these are chaotic systems. It means that a minor change of the conditions implies big changes in the results. The pandemic is an excellent example, okay? And it's also an excellent example of how we were able to recover. If you remember at the beginning we thought that several countries would collapse, several universities would collapse, several things, and actually somebody collapsed. But the institutions, many institutions were resilient, institutions and also commercial entities were resilient, and the shock helped us to understand what is resilience. But anyway, let me just show, okay, because I couldn't see in the screen, you cannot see, but the highest renewable water resources, the Brazil is the country with the highest percentage of, the highest, not percentage, the highest amount of renewable water resources. And renewable means something that can be reused. So hydropower, for instance, is renewable. And then there is Russia, USA, China, Indonesia. And I think we are done. There is one thing that I wanted to tell you. I mentioned that hydropower is essential, but if you saw the percentage is 3% of the global coverage of energy demands. Why is then hydropower essential? Hydropower is not only renewable, hydropower can be stored. And this is why it's essential. If you think about wind energy, you cannot store it. You have to take the wind when there is wind. Solar, same thing. You cannot store solar energy. And you may think of batteries. Batteries are absolutely not efficient. You cannot store electricity. You can store energy, but not electricity. So, in a way, hydropower, you can store the water and you can produce the electricity when you need it. So hydropower is filling the gaps. Hydropower is giving resilience. And there is another thing that is important. When you have excess of energy from wind or solar power, you can use the energy to bring the water up. So it is a way to store energy with a very efficient conversion, because if you use the energy, the electricity in a pump, the pump has an efficiency that now is about more than 85%, which means that you make a conversion of energy with an efficiency that is much higher of that of batteries. This is why water, surface water, is important, and hydropower is important. The countries that have a lot of hydropower have also resilience and have the opportunity to store the energy in excess by pumping back. And this system is widely used. Several of our hydropower farms pump back the water when there is excess of energy from other sources. Okay, let me go back to the PowerPoint presentation. I think we are almost done here. Okay, this is the global water footprint by sector. This is interesting. And it means that agricultural products are responsible for 72% of the global water footprint. And then there is industry, domestic products, and the external water footprint is, because this is the internal water footprint, the green one. The external water footprint at the global level, which means the total of imported goods, is about 22%, where agricultural products are 20% and industrial products are 2%. These numbers, they are interesting, but I'm not asking any question related on these numbers. Of course, if you remember that 70% of the water is used for agriculture, for food production, is a good idea, because try to just keep in your memory the big figures, not really the numbers, but the big figures, because otherwise, if you don't have the figure, water footprint is not so important. But when we talk about water consumption, it's important that you keep in mind the big figure, 70% used for at the global level for irrigation. This is, otherwise it's difficult to get oriented. Here I am already moving in the next lecture. Just let me check. I have 15 minutes to go. Let me check how many slides. Okay. And so let me just move. So I take a little bit of a break on the website, because there are some things that I wanted to say that are not. Okay, very good. And this one, it's a concept that I want to highlight. It's not highlighted in the slides. The classification of water flow, and try to remember this because it is important. So it can be classified in blue water flow, green water flow, and gray water flow. Okay, so the blue water footprint is the volume of water that has been sourced from surface or groundwater resources, lakes, rivers, wetlands, and aquifers. This is the blue water footprint, okay? And this has either evaporated. If we used it, what happens? It's either evaporated when we use water for irrigation, this blue water flow evaporates, and or incorporated into a product, chocolate, or taken from one body of water and returned to another, or returned at a different time. Okay, so irrigated agriculture, industry, and domestic water use have at least a part of blue water footprint. Okay. The green water footprint is the amount of water from precipitation that, after having been stored in the root zone, is either lost by evapotranspiration or incorporated by plants. So basically it's water from precipitation that doesn't reach the blue water flow, doesn't reach a surface water body. Okay. The gray water footprint is the volume of water that is required to dilute pollutants, industrial pollutants, or mining operations, etc., to such an extent that the quality of the water meets agreed water quality standards. What does this mean? When you produce pollutants, before releasing the pollutants into the final recipient, you need to dilute them to make sure that the amount of pollution has been reduced enough. And this is the gray water footprint. It is quite a large amount of water that is used in this way. An issue today is that with the expansion of agriculture, we have forced a blue to green conversion. So we are deprivating surface water body of water. You may have heard that the Colorado River doesn't reach the Ocean Pacific anymore, the Pacific Oceans anymore, because from, I think, in the past 30 years, they didn't have any water discharged into the ocean because they are using all the water upstream. It means that the blue water flow of the Colorado River at the closure has been annihilated and transformed into probably green water flow or gray, whatever. Okay? This is an issue. It's an issue because of the ecologic implication of the environmental impact of reducing the blue water flow. And here you see pictures of the total blue, green, and gray water flow. And you see that there are two patterns that you can recognize. The pattern of societal development. The countries that are more developed societally tend to have a higher water demand. And the second pattern is that of precipitation, of course. If you see along the equatorial belt, you see that the blue water flow is higher. And of course. And also, if you look at the other pattern, I don't do the, okay, the last one is the total water footprint. So you can recognize these two patterns, climate and societal development. And they are related because where there is more water, there is, not always, of course, but water, as I said, is a propeller for societal development. Okay, so I think that here we have, here there is a short discussion on climate change, but we will talk about climate change later. I think we can move to the next one. Do you have any question? Usually I don't take many questions on, I don't get many questions on these topics because they are quite descriptive. But I hope that I was successful in conveying to you why they are interesting and important. I mean, it's something that is really developing quickly, and needs to be really monitored. While I was teaching, I realized that some of the slides, like 2010, data from 2010, 10 years now, it's a huge amount. The past 10 years have been, I don't know if my personal perception, which is a little bit amplified, but my feeling is that really, if I go back to 10 years ago, I see a completely different situation. Also, my teaching has changed completely. Okay, let's go to sustainable management of water resources, and here is the picture that you saw in my slides. Distribution of water, we already mentioned this, 97% in the oceans, fresh water is 2.5%, but, let me explain how it works, this column, this picture. 3 columns, and each column moving from the left to the right is an explosion of the upper part of the left column. So the left one take fresh water and it's exploded in the middle column. So glaciers and ice caps, so the fresh water is 2.5%, fine. Glaciers and ice caps cover 70% of the 2%. And then groundwater and the surface water. Groundwater is 30% available. Surface water is 1.2. This is interesting, but there is something that I have to say on that. Interesting, because it looks like groundwater is much more than the surface water. Fine. Let's get the surface water, explode it here. Ground ice and permafrost is different than glaciers and ice caps. It means permafrost is the ice into the rocks, etc. Sorry?
Permafrost is the water and ice under the surface soil.
Yes, correct. And ground ice is the ice that is on the ground, but it's not part of glaciers and etc. 69. And then you have lakes. 20%, atmosphere, other things, basically, and you see rivers, 0.49%. It's a small percentage. And now, you may ask me, but how's that? Because water from rivers is important. It's a lot of our supply. And why is the percentage so reduced? Okay, and this, if I got this observation, I would say you capture the limit of this representation. This is volume, but when we talk about water resources, it's not only volume that is important, it's much more important the flow. So the water stored in rivers, it's only a little quantity, because if you look at the volume of water that is stored in the Po River, even if it's a very long one, and you take a picture, and you estimate the volume, it's a long river, but it's much smaller than what is contained into a huge dam, because the river is not very deep. But that water is flowing, which means that if you have 1 million of cubic meters of water into a dam, you get it, and that's fine, okay? And then it's gone. If you go along the Po River, the volume is not much, but if you start taking the water with a flow of about 2,000 cubic meters per second, then you get much more water from the Po River because it's flowing. So this representation, indeed, which is proposed by the USGS, the United States Geological Survey, and is used by teachers all over the world, is highly criticized by some scientists, because they say this is not a good representation. It doesn't give a useful sketch of the importance of the water sources. But still, I think I'm using it because I think it is interesting. And now let me refer to groundwater. Groundwater is flowing, but it's flowing very slowly. So even if it is a percentage that is so large with respect to rivers in terms of volume, the recharge time is so slow that at the end of the story, groundwater becomes, yes, important, but not so more important with respect to surface water to rivers, because if you look at these percentages, this is 30% and this is 0.49% of 1.2%. So it's something that is really nothing compared to groundwater. But still, when you go and see where is water taken from, you see that, for instance, in Italy, the majority is from groundwater, but also from surface water, it's comparable. If I look at the Emilia-Romagna region, it's comparable. It's higher, the groundwater resource, groundwater use with respect to surface water, but they are comparable. So keep in mind that it's these behaviors of the water to the importance of the water flow or the importance of hydropower because it's flexible. These are issues that from a technical point of view are really what you have to care about. Okay, and now I close with this picture. Let me just open it in a... I close with this picture today. Are you tired? I heard something like... yeah, I understand. But, I mean, from a technical point of view, it doesn't require a long study. So once that you lectured and you read the web page, I think it's important information, but it's easy to get, to grasp. This is the distribution of rainfall all over the world. And here I make my first important technical observation. And I close with this. This picture shows rainfall in what unit? If you look at the legend here, it goes, I look at the upper part because it's millimeter per day, from the white bar 0 to the dark blue bar 6 millimeters per day. What does this mean? In different seasons, it's a moving picture. What does this mean? 6 millimeters per day times 365, it's about 3 times 6, 2000. So 2000 what? Millimeters per year. So the scale goes from 0 millimeters per year to 2000, more than 2000 actually, 2500 millimeters per year. This is the amount of rainfall, yearly rainfall, from 0 to 2.5 meters per year. So I recommend you are an engineer, the orders of magnitude of your design variables. It's extremely important that you have them in mind. So I started from a trivial example 1 hour ago, the weight of a liter of water. Now this is not trivial. If I made a pool, I'm not sure. If I asked you, to each of you, how much rain do you get in a year in your country, I'm not sure how many of you could respond to this. For sure, I couldn't respond at your age, at your level of education when I was a student. So the question, how much rainfall do we get in Bologna in a year? The answer is from 0.8 to 1 meter. This is something that you have to get in your mind, and it's also the average of the world. The global average of rainfall is about 1 meter per year. If you look here, there are countries with the dark blue, there are countries with the white, and it's interesting to see once again the equatorial belt is getting the more of the rainfall. It's interesting to remember, and there is written somewhere in the web page, that the global average is about 1,000 millimeters, about 1 meter, something more. And also in Italy, rainfall is varying from about 600 millimeters per year in the south to the most rainy region of Italy. The most rainy regions are in the northeast, Friuli, more than 2 meters per year of rain. It's about 2.5 meters per year of rain. This is something really important. If you go after your degree, you take a job and you go discussing with somebody and you miss the order of magnitude, this is really bad. So it's really bad because it happened to me sometime. Like you go to speak with a worker, and then it happens that you miss the order of magnitude. This is a problem because the trust of people in you goes down, down, down. If they realize that you studied for 20 years and still you don't know what is the weight of 1 liter of water, or what is, if you talk with a technician working in agriculture, you don't know what is the rainfall depth in Bologna in a year. And this is a problem. And when you will study floods, just keep in mind what is the amount of rainfall that causes a flood. So 50 millimeters per hour, 50 or 100 or whatever. And if somebody tells you it rained 300 millimeters per hour and you don't know if 300 millimeters per hour is a lot, this is a problem. Okay, I stop here. Do you have any question? Also, those who are attending remotely, if you have any question, please step in. I don't get any question. Now I stop the recording. Okay, thank you very much.